the climate is such like it is very cold. Even then, we have Dr. Joshua Ernest from NITTR Bhopal with us today. He is professor and head electrical engineering department, electrical and electronics engineering department at NITTR Bhopal. He has an experience of more than 30 years, and he has worked in this area of wind power and technology. He has been a consultant to China Electric Power Research Institute, Beijing, for online wind power training program, and he was honorary professor of wind power courses of Uppsala University, Sweden. He had authored different books, 2 books on wind power plant and project development and wind power technology. So he has brought various informations which he had from he got training from Sweden. He himself will tell about him, and we have a model of a wind power turbine also here to show you. So I hand over the mic and the class to him. He will be taking class till 12 o'clock only. So I request all of you, he will take the class continuously without any tea break. So after 12 we can have the tea. Okay. So I request all of you to sit and attend the classes fully so that he has to go at 12 o'clock. Okay. So please bear with me and take full opportunity, full advantage of this opportunity. Thank you. Over to you, sir.
Good morning, everybody. It's a joy for me to be with you on this mode, and I bring greetings from Bhopal. I'll just introduce myself so that you know. If you know the speaker, you will be able to understand with what spirit he's also telling. Okay. This is my academic profile. I have a teaching training experience of 30 years and I have a bachelor's in electrical engineering and MTech in electrical machine design, master's in technical education, a PhD, a guest professor on wind power in Sweden, a PhD examiner of electrical engineering and renewable energy. I'm a PhD guide and I have published papers in the area of wind power and engineering education available on the internet. I've authored books on technical education as well as wind power. So the very first book was this one. It's competency-based curriculum, which is being now run as outcome-based curriculum in different places. So this is the first book that I wrote, and the next one was Technical Education and Curriculum Development in 2010. That was published by NITTR Bhopal. Then Laboratory Work and Assessment. That was another book which I edited, also published by NITTR Bhopal. This is the book. This is the copy or photocopy. I would not say it's a scanned copy of my book, first book. It was written by myself and colleague of mine, Professor B.L. Gupta. This is the book that on curriculum, based on curriculum and engineering education. This is on laboratory assessment. Then coming to my professional profile, I have an industrial experience of almost 6 years. First in India to offer online short-time wind-term courses. Consultant to China Electric Power Research Institute, Beijing, for the online wind power training programs. Was an honorary professor for wind power courses in Uppsala University, earlier called Gotland University, Sweden. I'm the convener of the first International Wind Energy Conference from 5th to 7th January 2006, and another one in 2011. Training national and international industry personnel in the area of wind power, author of technology books. The very first book was Wind Power Technology, Wind Power Plants and Project Development. This is in the second edition now. This is almost a textbook in Gujarat Technological University, then PhD College of Technology, Amrita University, and it is being given as a resource material by National Institute of Wind Energy, Chennai, which is the Government of India organization responsible for developing or promoting wind power in the country, and also encouraging research. This is a totally full color full color book, hardbound. So you can see all the photographs will be in color. So this book was written for the wind power industry, but it is being used by the university systems as well. And the other one is a black and white book. It's wind power technology. This was written solely for the university system. It is also in the second edition. Both the books are textbooks in various organizations and universities. So these are the scanned copies of the books. This is the first one, this is the second one, and it goes on like that. So now let's start the wind power course. Yeah. Okay. So when the winds of change blow, some build walls and the others windmills. That's a Chinese proverb. For any learning to be more effective and efficient, a picture is better than 1,000 words, and a video is better than 1,000 pictures. So all my PowerPoint presentations will be full of visuals, very less of written material. Whatever I'll be saying, you can write down if you want to understand it better. So I start with learning. I said learning has to be effective and efficient. What does effective and efficient means? Effective means if I am teaching you 100%, at least 90% you should be able to learn. Efficient means in the least possible time, the maximum learning should occur. So that's what is effective and efficient learning. So what do you understand by learning? Because basically we are in technical education, I thought I'll start this session with what is learning. Once you know that, then it will be much easier for you and for everybody to teach you also well. We see here a parrot and two friends talking to each other. One of them is telling, I taught my parrot to whistle. And his friend replied, but I do not hear him whistling. He laughed. Ha ha ha. I only said I taught him. I never said it learned to whistle. So what is learning? Learning means there has to be a change in behavior. If there is no change in behavior, learning has not occurred. So you may teach as long as you want, but if the student does not learn, then we are not effective and efficient in our teaching. So with that note, I go to the next Chinese proverb. It says, the more I hear, I forget. More I see, I remember. More I do, I understand. So any technology or any learning, unless you do, that means you get involved in the activity yourself, then you will be able to understand. Otherwise, you will hear this and you will forget. So I am not much in favor of these talking head lectures because it is more of an information and you'll forget many of the things. I always prefer a face-to-face, on-the-job learning so that you will remember for a longer time and there will be a change in behavior. But anyway, this is one of the modes. I would say that you will have to continue on whatever I have showing you to read from various books, do some projects on wind power, give the students small projects on wind power. That's how you, along with the students, will also be able to learn. So at the end of the session, you would be able to differentiate the various types of wind power plants. So I would start with a video first of all. This video has been produced by Nitar Bhopal, and it is available in our institute. Any institute which wants to buy it can buy it if you want a good copy, because this will of course be going on YouTube, but then anybody else would like to have more copies of it are welcome. So let's see the video first. Open with हाँ हो जाएंगे ओके it's not coming full time.
I don't know. Is it?
But I want the full screen.
Center wala three options are center.
Okay.
Yes.
Hello viewers. In the previous part of the series, we have seen how the wind turbine nacelle is assembled at the factory. The assembled 500 kilowatt nacelle weighing 22 tons and the rotor hub weighing about 2 tons are then transported to the wind farm site for installation. In this program, we shall see the construction of the wind turbine foundation, erection of the lower part of the lattice tower, attaching the upper part of the tower, raising the nacelle to the top, assembly of the wind turbine rotor, and hoisting and attaching the rotor to the nacelle. Let us see the process of installation. At the wind farm site, the foundation work of the wind turbine tower commences, and here it is done both manually as well as mechanically. Since this is a lattice tower foundation, the 4 legs of the lattice tower will rest on the 4 foundation footings. The size of the square foundation pit required for a typical 500 kilowatt wind turbine tower is 8.4 meters by 8.4 meters. Measures 11.37 meters diagonally and is 5.8 meters deep. The 4 foundation footings are resting on the foundation base, which are being constructed with reinforced cement concrete. This is where the expertise and the competence of the civil engineer comes in. The water in the pit is for curing the foundation base. The steel reinforced foundation footings are filled with the cement concrete and cured for about 21 days. After the long journey from the factory, the rotor hub and the nacelle reach the wind farm site. The aerodynamically designed 23-meter long wind turbine blades weighing 1.5 tons each are also brought. Due to its huge size, length and weight, Each blade needs to be transported separately to the wind farm site. In case of steel tubular tar wind turbines, the giant parts of the tubular tar and the nacelles are transported to the site by road. The 500 kilowatt nacelle and hub are unloaded at the spot. Huge cranes and skilled manpower do this task. After 21 days of curing of the RCC foundation base and footings, it is time for refilling of the excavated pit with the soil. This is where the dozer comes into action to level the pit. Now, the foundation base is ready for installing the tar. For installation of the lattice type steel tar, varied length steel angular sections are used. These steel angular sections are assembled to build the tar in two parts, the lower part and the upper part. Usually, the installation of a wind turbine starts in the morning hours so that the installation up to the nacelle level gets completed by sunset. Generally, two cranes are required for the construction of the tar. A big one with a boom length of 60 to 70 meters and a smaller one having a boom length of 20 to 25 meters. The lower part of the tar is assembled and ready for installation. It measures 25 meters long and weighs 22 tons. For hoisting this, the skilled workers attach the hooks of the small crane to this tar base. Next, the upper portion is hooked by the big crane for hoisting it onto the foundation bed. Simultaneously, both the cranes are operated so that the tar gets lifted from the ground slowly and safely. You may note that the upper portion gets lifted faster than the lower portion. This renders it in such a way that the tar hangs suspended by the bigger crane. As soon as the tar becomes vertical, the hooks attached to the small crane are removed. The big crane then slowly moves the suspended part to the foundation bed. The tar is aligned to the foundation base. Steel flange plates join the tar and the foundation base. Bolts are inserted through the flange plates and steel angles for the nuts to be tightened. Wrench spanners are used to apply the same torque to all the nuts and bolts. This activity is done simultaneously for all the four legs of the tar to securely fix it to the foundation bed. Next, it is the turn of the upper part of the wind turbine tar to go up. This is 23.1 meters tall and weighs 18 tons. Hence, the crew gets ready to climb to the top. The required tools are carried along with them. Adequate safety precautions are taken while climbing the tar. On reaching the tar top, the workers loosen the relevant nuts and bolts to release the crane hook. is now time to make necessary preparation to receive the second part of the tower. The second part is assembled on the ground and ready to be hoisted. As before, relevant crane hooks are attached to this part to hoist it. Now, this tower section is slowly raised from the ground. The big crane lifts the upper portion faster so that it gradually gets vertically suspended. As soon as this tower section becomes vertically suspended, the hooks of the small crane are released. Both the rope crews control the undesired movement of the suspended tower part as it moves up. The big crane then takes the upper part of the tower still further up and up. The crew on the top eagerly waits to receive as it comes up. The upper part is gradually moved nearer and nearer to the installed part with strict control of the crane movement. When the upper part of the tower reaches the top, it is aligned and inserted between the steel flanges and angle plates. The crew insert the bolts and the nuts are tightened using wrench spanners as was done on the ground. The hook attachment of the bigger crane from the tower top is then released. The tower now stands at 48.1 meters and is ready to receive the nacelle. Before lifting the nacelle of 22 tons and diameter 2 meters, the main shaft flange is clamped so that it does not rotate. The nacelle gets lifted from the ground. As the nacelle rises, the rope crews control the undesired movements. The crew on the top eagerly awaits to receive the nacelle, which is being gradually lifted towards them. The coordination between crew on the tower top, the rope crews, and the crane operator hoisting the nacelle is of utmost importance for the safe installation of the nacelle. The yaw ring of the nacelle is going to be fixed on the tower top. No sooner the nacelle is placed on the tower, the crew enters it from its bottom hatch to bolt the yaw ring to the lattice tower. This enables the nacelle to rotate around 360 degrees in the horizontal plane to face the wind. Once the nacelle is bolted securely, the hook of the crane is released from the nacelle. The total height of the tower is now 48.1 meters. With the nacelle on the top of it, the hub height is 50 meters. Now it is the turn of the rotor to go up, which has to be assembled. In this case, the hub also contains 3 pitching lever mechanisms. Each of them is attached to a blade in order to turn it longitudinally by an angle of maximum 90 degrees. To assemble it, the rotor hub is placed in such a position that each blade can be attached to it without touching the ground. The nose cone, made of glass fiber reinforced polyester, that is GFRP, covers the hub for protection against rain and sun. The rotor blade rests on the truck to be picked up. The blades are made of glass fiber reinforced polyester to render them as light as possible and to increase their longevity. A specially designed T-shaped blade lifting device is used to lift and carry the blade to attach it to the hub. The root of the blade is to be inserted through the nose cone. As the blade root reaches the cone, one group of skilled workers takes position inside the hub, while the other group waits outside. Both groups coordinate the attachment of the blade securely to the hub. The workers inside the hub attach the blade using long bolts, which are well greased. The pitching lever mechanism inside the hub is also bolted to the blade root. The other two blades are also attached to the hub in the similar sequence of activities as seen for the first blade. The blade tip is well protected by soft material to save it from damage when handling. Once all the blades are attached to the hub, they are feathered to 90-degree position. This is also the aerodynamically braked position of the rotor. This blade position prevents the rotation of the rotor during hoisting operation and thereby avoid accidents. The gray spot at the tip of the blade is one end of the lightning conductor. It runs all through the hollow length of the blade and ends at the blade root, which is electrically earthed. This protects the wind turbine against lightning strikes. Generally, lifting of the rotor onto the nacelle is done either early in the morning or late in the evening. During this period, the wind speed is relatively slower than the rest of the day. Now it is time to call off the day. It's early morning and the erection crew is ready to hoist the assembled rotor. One installation crew, which has reached the nacelle on the top, is waiting for the rotor to come up. The big crane will pick up the rotor hub by a specially designed clamp. The soft material loops are used to hold the blades by the crew and the crane while lifting. As the rotor rises, again the rope crews restrict the undesirable movements of the rotor for safe installation. You will note that the small crane is holding one of the blades to avoid it hitting the ground when the rotor gets lifted. The coordination of the rope crews with the big and small crane operators is quite critical for lifting the rotor safely. At this point, the communication of the nacelle crew is also crucial for the proper alignment and attachment of the rotor to the main shaft of the nacelle. Again, it may be noted that the rotor is parked by the aerodynamic braking of the blades. That is, they are pitched at 90 degrees. So viewers, in this program we have seen the construction of the wind turbine foundation, erection of the lower part of the lattice tower, attaching the upper part of the tower, raising the nacelle to the top, assembly of the wind turbine rotor, and hoisting and attaching the rotor to the nacelle. In the next program, we shall see the different features of wind turbine and electrical substation and how the wind turbine produces electrical power from the wind. Until then, goodbye.
Well, friends, hope this was one type of wind turbine or wind power plant that was shown to you. Hope by this time you would have realized that a wind turbine is a highly interdisciplinary area where a lot of engineering technologies get merged. So that's what we are going to look at now. Okay. So wind power is not a new concept, as you all know that. Right from the Persian times, the Persian grain grinding windmills were used to grind the grain. The Chinese used them for irrigation using the wind wheel. But the development of power electronics, digital electronics, computers, aerospace engineering accelerated the wind power revolution in the world and in India as well. So that's what we'll be looking at it in the coming slides. What are the modern wind power? How do the modern wind power plants work? There's the wind, which has the kinetic energy. That kinetic energy is converted to mechanical energy by the gearbox, and the mechanical energy is converted to electrical energy by the generator. And different types of generators are used in wind power plants that we'll be looking into later. And then that is transmitted to the grid. So the first part is called the primary energy conversion, and the second part is called the secondary energy conversion. How did this all begin about? Thanks to 1973 oil crisis, which gave the push to the development of wind power plants, and also thanks to the advancements in electronics engineering, power electronics, computer technology, mechanical engineering, instrumentation engineering, aeronautical engineering, and civil engineering, and others as well. So there's a lot of scope for research in the area of renewable energy, especially wind power. And any engineering or any engineer can do some research, do his PhD, do his MTech dissertation or thesis as well. What are the advantages of wind power? Many of you must already be knowing about it. The wind blows day and night, which allows wind power plants to produce electricity throughout the day, faster during the day especially. No fuel is required, no water is required. There is zero pollution. The carbon dioxide emission is also reduced. The cost of wind power has reduced because a lot of research going into it. Almost all investment in India is from the private sector. So that shows that wind power is technology which has been commercialized well. Higher rural employment leading to higher GDP growth. The reason being, most of the wind farms are in the rural areas and not in the cities, and therefore a lot of rural employment takes place. Now, as the rating of the wind turbine increased over the years, the term wind underwent metamorphosis. There are various terminologies on the internet and other literature, but by and large they mean the same. So I'll just introduce to you some of the terminologies that will come across. The wind energy converters, or WECs. The Danish people were one of the pioneers in modern wind turbine development. Therefore, WECs was the term that was used by the Danes. Then the Germans came in, they also followed. They called it wind electric generators. Then the British named it as wind turbine generators, followed by the Americans, which use just wind turbines. They call it wind turbines as well. Now the term WPP, or wind power plants, is becoming popular as large ones of megawatt range are becoming more and more common in India and around the world as well.
प्रॉब्लम असा होता. कैमरा ही चला गया।